Hi everyone, I'm Chuhong. Thanks for the previous speaker. Give some introduction about the condensates in the transmission spectrum. So today I'm going to talk about my work on exploring the cloud assumptions of exoplanets with JWST transmission spectrum with my client. So the atmosphere of an exoplanet is the portion that is most readily observable, and the characterization of the atmosphere can tell us almost everything about the planet, including the potential habitability. A very important component of the atmosphere is the clouds. Clouds almost exist on every solar system planet that had an atmosphere and have been observed on exoplanets. It is very important because they have high albedo that can affect the energy balance, and they can also infer the temperature profile and atmospheric dynamics. But the thing is, for now, we don't have enough knowledge about cloud properties through the current observational data, and we do hope to learn more about it in the future. So in this talk, our goal is to explore how much information and what kind of information about cloud properties we can get from the future James Webb Space Telescope. The data I'm talking about is the transit transmission spectrum. A lot of you should be familiar with this concept, but since I have this slide, I will just walk through a little bit. So when a planet orbits in front of its host star, transit occurs. Because there are many different gas species in the atmosphere, they can absorb the starlight at different wavelengths. So we can observe the planet radius or the transit depth varying with the wavelength, and that's what we call a transit transmission spectrum. A transmission spectrum is essential in helping us to constrain the existence and the boundaries of chemicals in the atmosphere, and it can also, for potentially habitable planets, it can also check the biosignatures or biomarkers to help assess the planetary environment. But everything changed when clouds exist. So clouds are very confusing in the transmission spectrum. Due to their high opacity, they tend to block out a lot of the starlight that can smear out the absorption features of the gas species. So, but hopefully, with the launching of the James Webb Telescope, we can better characterize clouds in the transmission spectrum with higher resolution and signal-to-noise. This figure shows the major instrument and the wavelength coverage of the telescope from visible to mid-infrared. To do the better characterization of clouds, we better first know what degree can JWST tell us about the cloud properties. So to constrain cloud properties from the transmission spectrum, we first need to know what clouds can do to the transmission spectrum. So we use a radiative transfer forward model with the inputs of gas, gravity, temperature profile, and clouds to create a simulated transmission spectrum. And the instrument model can noise up this transmission spectrum to mimic the real observational data, and in this case, the JWST transmission spectrum. And then we can go ahead to fetch the information of cloud properties from this fake data, and we'll use a Bayesian retrieval method to do it. In this study, we don't care about other inputs. We only focus on the cloud parameters. And we want to have a parameterized clouds that is physically well-motivated and also observable. So we use 4 parameters to describe the cloud in the model. The pressure level, where the cloud base is, and the mixing ratio of the condensates at the cloud base pressure, and vertical profile index alpha to describe how the mixing ratio falls off with the high altitude. And also there's one more parameters to describe the particle size of the cloud condensate that is closely relevant to the optical properties of the condensates. So in summary, in our forward model, we include 15 gas species. And currently we are assuming typical atmospheric parameters for hot Jupiter HD 209458b. Note that we did not start with Earth-like planets because they are difficult in observation, and hot Jupiters are expected to more rich in terms of data. So our first goal is to take a first glance of what can we learn about clouds from transmission spectrum in the case of a hot Jupiter. And on top of these assumptions, we add the parameterized clouds that we just described. So with this input and through the forward model, we're able to generate the fake transmission spectrum of JWST. Here we assume a cloud composed of anstatite MGSI of 3 with particle size of 0.1 micron. The cloud, oops. The cloud-based pressure is 10 to the minus 2 bar with a mixing ratio of 10 to the minus 13. The cloud extends all the way from the cloud base to the top of the atmosphere. The blue line shows the simulated transmission spectrum, and these black dots with error bars are the fake data points we made. The red curve shows the contribution from the gas species, and the green curve shows the contribution from the cloud condensates. Note that the cloud mainly affect the transmission spectrum at short wavelengths with a Rayleigh scattering-like feature, and also at longer wavelength with a resonance feature. Then we can go ahead to fetch information from this fake data we made using the Bayesian retrieval method. That we know the Bayesian retrieval is based on Bayes' theorem, that we know the likelihood function, the prior distribution of parameters, and the evidence. We can go ahead and derive the posterior distribution. To be more straightforward, the Bayesian retrieval is to constrain cloud assumptions from the fake data. So now we already generated the fake data, which is cloudy, from the forward model. And now we're going to pretend we're ignorant about the cloud properties. So we designed experiments to test different cloud assumptions. To do that, we need to set the targeted parameters that we want to know free and let the retrieval model to find its best fit, which is the posterior distribution. In our first experiment, we test the cloud-free model on the cloudy fake data to see whether we can tell cloud exists from this data. We choose temperature, metallicity, C/O ratio, and the planet size scale as the targeted parameters. And this is the stair-pairs plot of the posterior distribution of these parameters. From this comparison table, we can see that the best fit values of these parameters are all far off from their true or input values in the forward model. And then we can also take a look at the feeding. This blue line is the feeding curve of the retrieval, what is retrieved from the retrieval model. And the green dots are the fake data points. We can totally say this is a very bad feed and the chi-square is very large. So the conclusion is that we can definitely tell cloud exists from the data we have. In the second experiment, we retrieve the parameterized cloud model on the cloudy fake data. Besides of the previous 4 basic parameters, we also add the 4 cloud parameters to be retrieved. I apologize for the very small labels in the stair-pairs plot, but we can focus on the comparison table that these parameters being retrieved, their best fit values are very similar to their input values. And if we take a look at the fitting curve, we can say this is a very good fit with a small chi-square, that we can conclude that the cloud parameters are well constrained from the data we have. In the third experiment, we test the gray cloud model on the cloudy fake data. The gray cloud model is a simplified cloud model that uses 3 parameters, the cloud top pressure, the haze amplitude, and haze slope to mimic the what usually the effects of clouds have on transmission spectrum, that is a short wavelength slope and a flattening effect in the longer wavelength. And in the table, we can see that temperature, metallicity, CTO ratio, these important atmospheric parameters, they are all deviated from the true values for the forward model. But if we take a look at the fitting curve, the situation is actually not that bad. Chi-square is not that large, that is not very unacceptable. The fitting, we can say it is good enough, but if we only look at this fitting, we might get tricked because the gray cloud model is providing us a very wrong information of the atmosphere while feeding the data not very badly. So at the current stage, we have some conclusion, but actually more questions. In a specific case we test against, we conclude that we can tell cloud exists, and the cloud properties can be well constrained from the fake data we made. But however, record that the cloud we choose generate a resonance feature in the long wavelengths. That itself might be very unique, that can help the cloud properties, the cloud parameters to be well constrained. So we can ask the question like, what if we only look at the short wavelengths? What if we choose something else that does not generate this resonance feature? That is especially for condensates on Earth-like planets. Another conclusion is that the gray cloud model, which is popular in atmospheric modeling, it is actually dangerous to use, at least in this case. So, but what if we had a big particle-sized cloud coexist with a small particle-sized cloud? That is what the case that usually the gray cloud model is trying to mimic. Would it provide correct information of the atmosphere? So these are all the questions that we hope to explore more in the future. We actually have a lot more experimental runs to come to answer questions like, can we constrain particle size of condensates from data, and can we tell there's a second cloud exist? But more importantly, we will also start the series of experiments on the case of smaller and cooler planets with the same methodology. Thank you.
We have time for 1 or 2 questions.
Great work. You might want to look at how your constraints vary with the specific instrument spectral range that is appropriate for different JWST instruments. Mm-hmm. For example, near spec only has several gratings, 2.5 to 5, so forth and so on, and you could examine how your constraints benefit from different observations, because you will never get that spectral range at one time. So the question is how it depends on what instrument you're using.
Yeah, thanks.
We could possibly take one more quick question.
I have a quick question. In the retrieval that included the cloud model, it seemed like the cloud pressure base wasn't well retrieved. Are you just insensitive to the base of the cloud?
Yeah, actually, due to the time, I skipped that. Yeah, it's not well retrieved due to a very specific reason, just in this case. So it is actually because of an effect called a cloud-based effect that generate a dip in the transmission spectrum, and that feature is deeper than the water feature. So when they overlap, it kind of can't tell what a cloud base is. So if you want more details, I can explain later. Yeah.
Thank you. Let's thank Chuhong
again.